So what we want to start with is this idea of molar heats of fusion and solidification. Okay, so we see here we have our delta H of F, so that's your enthalpy of fusion, which is basically melting, and we also have the enthalpy for solidification or freezing. Okay, when we're dealing with the heating curve, we know that we can solve for energy change along that heating curve. And I'm going to draw it up on the board for you guys now. In our normal heating curve, we have 1, 2, 3, 4, 5 different legs of our heating curve. Okay, we go anywhere from a solid to a liquid up to a gas. And previously, we were able to determine what happened in these 3 legs of our heating curve. So when you warmed up a solid, warmed up a liquid, or warmed up a gas, or cooled them, anytime we had a temperature change, we had an equation to solve for energy change there. And an equation was MCAT, okay, where we had the specific heat capacities and the change in temperature. However, at these flat lines, segment 2 and segment 4, we can't use this equation because we don't have a change in temperature. So instead, we had to use molar heats of fusion and molar heats of solidification. Okay? Basically, we had to use the enthalpy change during that process. So at line 2, when we're converting from a solid to a liquid or a liquid to a solid, either melting or freezing, we say that the energy change is equal to the change in enthalpy of fusion times the number of moles we have. Now we need to multiply it by our number of moles because this value in here is actually labeled kilojoules per mole. And we want to solve for energy. Remember, Q is energy, so it's either going to be kilojoules or joules. So we have kilojoules per mole. So to get energy here, we need to multiply our enthalpy value times moles so they cancel out. Okay? So however many moles we have here to do that. Now when we're going this direction on the heating curve, we're putting energy in. So we're actually melting, or we're fusing is a fancy term for melting. Okay? So when we're putting energy in, our delta H of fusion will be positive. However, if we were going this direction on the curve, we're freezing something, which means we're releasing energy. So the same amount of energy change is present, but because we're exothermic, we now make that value negative instead. Okay? So as you see on the screen, 2 equations, the only real difference is we have negative sign for freezing because this will be a negative value instead. Okay? The exact same thing applies to heats of vaporization and heats of condensation. Exact same equations, we just need to look up a different enthalpy value on a table. Okay, so these enthalpy values will be given to you in some sort of table. We actually have a thermodynamic reference chart that's in your notes so you guys can use to do that. So when you vaporize, going back to the board, same idea. At stage 4, we have to solve for the Q being the change in enthalpy to vaporize times however many moles you have here. Okay? So again, same equation. Here you're looking for heats of fusion with an F. Here you're looking for heats of vaporization. Okay? Now, one thing to keep in mind in terms of signs, anytime we're dealing with enthalpy changes that are exothermic, make sure that you're making those negative numbers. Anytime you're dealing with enthalpy changes that are endothermic, we want to make sure that that enthalpy change is positive. Okay? As we're working through these. Now, if you take a look at this table, this is a table that's in your website. It's on the website. You have access to. We may even have this exact same table on our test coming up. It gives us these different values. So here's your heats of fusion in kilojoules per mole, labeled out for all your different substances. Here's your heats of vaporization. Okay, so what I would maybe do right here, because fusion isn't a word we're real comfortable with, maybe change that or write melting by this. And then above it, write freeze and put a negative sign there. So remind you that if you're going to freeze something, that this is a negative. You got to pull these numbers off and make them negative. Same thing over here. Heated vaporization, maybe above that write the word condense and put a negative sign by it. So it reminds you that when you're condensing, it's the same number, we just make it negative. Okay? So a couple of questions for us. Why do we need the boiling and melting points? We have melting point here and boiling point here. Okay. Well, if you think about it, we know that water melts at 0 and boils at 100. So we know that this flat line is at 100 and this flat line is at 0 degrees C. For any other chemical, however, we don't know that. So if we're dealing with energy changes with ethanol, for example, and we're changing the temperature of ethanol, it boils at 78.4 degrees Celsius, not 100. So its flat line is going to be in a different spot. Okay? So if this was ethanol, this flat line would be at 78.4. This flat line would be at a negative 114 degrees Celsius. Which means your range between here is going to be different than water's. It means that the point at which you have to do this equation is going to be different, okay? So it allows us to find those breakpoints, or allows us to find our flat line spots on our graph, so we can calculate the proper energy changes there, okay? Now, we already talked about this, but how would these values change if we were condensing or freezing? Okay, remember these values would become negative instead on this table, okay? This table also includes specific heat capacities for you, so if you're doing a problem with this, you have all those values on there. So let's do, here's a real quick graph of our heating curve. Everything I've already drawn on the board is here. So as you guys are working through the notes, if you saw this, hopefully you were jotting things on this. Otherwise you drew your own heating curve in terms of that. The heating curve applet we've already seen in a previous unit, so we're not going to go back to that again. Just keep in mind that all these angled spots at part A, C, and E, we use the MCAT equation, and at D and B, we need to use the molar heat values to solve for those calculations there.